Ultimately, why do we care about traffic noise in particular? The bottom line is it's really probably the most pervasive environmental noise we're faced with. Not so much because it's loud, but because it's everywhere. It's almost impossible to escape. Also, it's expensive. There's a lot of dollars spent on abating noise, particularly in the terms of sound walls. It's also a major quality of life issue. If you live near a noisy road or a highway, it will definitely impact your quality of life. And also there's been links to health risk from traffic noise exposure. Okay, a way to illustrate that is my first audio example here. The question is, which of these would you like to live next to? Oops. You can tell the second one is quite a bit quieter than the first. And actually it doesn't show up here on this slide, but it's about a 9 dB reduction. For those of you that don't deal with dB too much, 3 dB is usually called noticeable, and 5 dB is typically what's used for noise abatement criteria for being a significant reduction. You might ask, why haven't regulations worked? Automobiles have been regulated for some time. Unfortunately, the test procedure is really geared at powertrain noise. And the test itself is low speed under full throttle acceleration, so it tends to be dominated by engine noise. Also, the test surface used is a relatively quiet pavement, so it tends not to emphasize tire noise. There are new procedures being developed, though, or starting to be in practice now that will address tire noise more, and also there's efforts at tire noise labeling and that sort of thing. So eventually all these things will help, but the biggest problem is that there is a wide range of level that's produced by different pavements. This kind of illustrates the pass-by noise contributors. This is data taken by the Federal Highway Administration in the US. The green line shows non-accelerating vehicles or cruising vehicles on an average of many roads. These are thousands of vehicle pass-bys. The blue line shows vehicles under acceleration. Now, the pass-by procedures we have that regulate vehicle noise tend to deal in the area of around 50 kilometers per hour, so it's kind of bringing the blue line closer to the green line as tire noise or engine noise becomes lower with these regulations. The brown line there is basically a typical fit for tire noise, which is in this case about 40 log the velocity. So what you can see when you compare the green and the brown lines is that under cruise conditions, it doesn't take very long until the pass-by noise level is dominated by tires as opposed to engine noise. The same thing is true for trucks. This is an example of some beamforming that we did recently that was geared towards looking at noise sources on heavy-duty trucks. And this is A-weighted contour, so the yellow is the higher levels. And what you find in terms of this A-weighted level contour is that, in this case, the drive axle tires are one of the dominant sources, with possibly some engine noise to the front of the truck. And also, interestingly enough, the trailer tires at the back are equally loud to those in the front. So this just emphasizes how much tire noise is a role in truck noise also. This is going to be kind of an outline of what my presentation will be today. I want to go through the phases of quieter pavement implementation. And this is semi-universal, I think, in listening to presentations and talking to people in other parts of the world in terms of the steps you go through for that. The first step is really awareness, and for a lot of people that's already happened. They know there are quieter pavements and it can affect traffic noise. One of the big implementers to this, though, was the book I'm showing here by Ulf Sundberg and Jörg Yes, Mott? This book was published, I believe, in 2002, and I've seen it now in almost every Department of Transportation pavement engineer's library or on their desk someplace. So it very much was a big impact on the field, I think. And I should say there's almost everything you ever wanted to know about tire noise in this book, except maybe the answer is what causes tire noise. And that's only because there are so many different mechanisms, and it's a very complicated topic. Varies with pavement, varies with tire design, on and on. The next part of implementation is actually coming up with measurement methods. To actually start to look at using quieter pavements, you need to know how to measure it. So that's the first step. The next typically is surveys. So once you have a measurement method that's proven and standardized, you go out and measure a lot of different roads to find out what the pavement's different levels are. This can be done in different places, but typically agencies will do it in their local area because those are pavements they know they can build if they find a quieter one. And also they'll do surveys, more academic surveys to look at what's been done in the literature and report it elsewhere. After the surveys, they pick quieter pavements, and they usually end up doing demonstration projects or research projects to see how much noise reduction they can actually get by using a quieter pavement. And after that comes the next, the more tedious one, is longevity studies. How long does a quieter pavement stay quiet? And that's a really big issue. And finally, once you've addressed all these things, you come up with an implementation strategy. How am I going to take these elements and combine them into a systematic way of looking at noise abatement? So kind of what's the big deal? It's easy to go out and measure highway noise, just as shown here. Put a microphone up alongside the roadway, let vehicles go by, measure what the noise level is, change the pavement, and do it again. Sounds real simple, but the problem is that the vehicle speeds may change, the traffic mix may change. There's a lot of variables involved. So actually, to assess the role of the pavement, you need to do a couple things. You need to isolate the tire noise in particular, and we do that, first of all, by looking at individual vehicles. So, and this is done by looking at averages of different vehicle classes, measuring pass-by noise, typically at 7.5 meters away from the vehicle. So in that case, we can know how much noise a truck would make, how much noise our car would make on average. And the next step then is to isolate the tire noise. These vehicles, as I showed you with the truck, there is noise sources other than just tire noise. You need to know how much contribution is tire noise versus other sources on the vehicle, and then relate that to the pavement. So there are procedures to do that. I'll look at this as what I call a roll down of measurement methods. You start with the traffic noise, isolate individual vehicles and look at those statistically for noise, and then ultimately look at the pavement by measuring tire noise at the source. And there are standards that help us along the way. Pass-by standards are some in the U.S. under an ASTRO procedure, and then also an ISO, statistical pass-by method. And for tire noise itself, there are two methods that are used pretty much worldwide. And these are tire noise measurements made at the source. The one on the left there is what's called the CPX, close proximity method. It's an ISO method. It measures sound pressure, and it can be done either on a trailer, closed trailer, or an open trailer, or on a vehicle. On the right is the OBSI, or sound intensity, onboard sound intensity method. And this is measured somewhat similarly with microphones traveling with the tire on a vehicle, with the difference being that it measures the vector of sound propagating away from the tire, not just the sound pressure. Okay, now that we have some measurement methods, next thing to do is hit the road and go out and start making measurements everywhere you can find a pavement that you're interested in testing. So this was done initially in the west of the U.S. and California and Arizona in particular, but this is not unique. Other state agencies in the U.S. have done this, as well as other road ministries across the world. In this particular database, we see a range in noise levels. The darker blue is generally the quieter pavements. These are open graded and rubberized pavements in this part of the country. The lighter bars are PCC or concrete, what we just normally think is concrete pavement, and the gray bars are what's called dense graded asphalt. This database is a little bit limited in terms of pavement type just because of what's in that region. For that reason, the next step that we did was to actually take our test procedure, the OBSI procedure, to Europe. Back in the fall of 2004, there was a lot of interest in the U.S. to examine some of the quieter pavements in Europe. So we did that. We measured in 4 different countries, a good number of pavements of different types, and completed that. What we found is shown here. The lower right is the similar kind of results from the European database compared to what I showed you before for California and Arizona. The thing to note here is that the range in terms of quietest to the noisiest pavement is about the same. It's about 13 dB. Now, some of these pavements aren't common between the states that the database was from and those from the European countries. So there are more of those in the Europe area. One thing in Europe at that time, they weren't using rubberized pavement, so we weren't able to test any of those. But in the California database, there was no stone matrix asphalt, which is common in other parts of the U.S. and certainly Europe and other parts of the world, but not in the West. So the other thing you'll notice is that there are some really quiet pavements here. And I flagged those because these are double layer porous pavements, and we'll be talking about those as we go on here. But these were definitely world-class in terms of quietness. There are other pavements now that are being developed. I'm not quite sure I'd call them pavements, but essentially rubber-based, where the whole pavement is a rubber-based product. So this is our current database, and this is pretty much limited to the West Coast again. And it's just a pretty plot, so I thought I'd put it up there. But it shows all the colors that we've, and pavements that we've measured. But what you can do with this sort of database is then look at pavements as a group. On the left here are the asphalt pavements as a general group, and on the right is concrete, PCC. And what you can see in this is that the range is about the same, and actually if you look at the averages, which are the corresponding blue bars to the right of each data set, the averages aren't that different. They're about, well, 101 and 102 decibels. So, but what you do see is that the range is different. The concrete surfaces, the quietest, is a little less than 100 dB, where for the asphalt surfaces, they're approaching 96. So there is some potential of getting quieter pavements, both in terms of asphalt pavements and also in terms of concrete. Also, this is a good point of reference to understand what we talk about when we talk about quieter pavements. It's all relative. It really depends on where you start. So if you start with a very noisy concrete pavement, as I'll show you later, and then overlay that with a quiet asphalt, you'll get a big reduction, as this data would indicate. So what makes a pavement quieter? And I'm just going to give you the high-level view here. On the right, you can see this is actually a test surface from a manufacturer's test track designed to make a lot of tire noise, and it does. It's 110 decibels, and it's even louder inside the car. On the other hand, the low texture pavement is actually at the same site, but this is a smooth asphalt pavement, relatively not a lot of texture in it, and you can see the levels are 15 dB quieter, which is pretty amazing. Of course, the pebbly surface is pretty amazing in itself too. As far as the other aspect of pavement that makes it quieter is porosity. What's shown in the lower left there are 2 pavements that are essentially the same mix of sizes of stone or aggregate in the pavement, and we're seeing, even though they are the same in terms of those kind of properties, the porous pavement on the right of those 2 is about 2 dB or 3 dB quieter than the non-porous. So one metric of this is looking at aggregate size. As this plot shows, generally as the aggregates get larger, the noise goes up. And some of the quietest pavements are ones where we have very fine aggregate, which is shown by the aggregate size on the bottom of the chart there. But that's the simplistic view. It's more than just texture. It's really what direction the texture is going. Is it plus or minus? Plus means that the aggregate is sticking up from the pavement, so it's basically, when the tire goes over it, this provides an input to the tire, a vertical input to the tire, which ultimately gets radiated as noise. The other extreme is negative texture, where essentially the top surface is relatively flat, but the texture goes into the pavement. In other words, there's voids in the pavement, negative from where the average surface is. So that double layer porous that I showed you earlier takes the best of both worlds. It actually puts a finer aggregate on the top of the surface, as shown here, and then a larger aggregate on the bottom. And what this does is it provides a lot of drainage through the pavement. So these pavements are also really good for splash. In other words, if you're out in the rain, you definitely can see a lot better when you're on a porous pavement than if you're on something that's not porous. And the levels are low. And it is a much more complex design and has costs associated with it, but also it does can produce lower noise levels, quite a bit lower. So turning to concrete, to PCC, what makes that quieter? It's primarily texture. And what I'm showing here is 2 or 3 different kind of common types of texturing. The first 2 are what we call transverse tining, where they actually take a rake or some other device and drag it along the pavement and create these grooves that you see here. Even within that, though, there are a couple of differences. The one here is what's called a uniform transverse tining. Oops. This is a random transverse tining. So I think you can tell it's a little bit louder than the first one. And then finally a longitudinal. This time the grooves go in the direction of travel. And that is definitely a quieter pavement. So, and this is getting to be a very common surface treatment now for concrete, because it's relatively inexpensive. There's no added cost to doing the tining, and it is quieter. These can be grouped. There was a study reported some time ago now looking at basically another survey, going out and measuring pavements in a lot of different places and looking at what these texturing effects do. The transverse is certainly the highest grouping, and what's called diamond grinding, and I'll have an example of that shortly, is the quietest. And that gets down to what you'd really probably call a quieter pavement in terms of for concrete pavement. So what makes a concrete quieter? Less texture, just like it is for asphalt, and also, as we just saw, the direction of tining. But it goes, that's only up to a point. If you look at these 2 pavements, the one on the left is what's called a burlap drag pavement, where they actually take a piece of burlap, drag it across the pavement, and come up with that texture. The lower right, though, appears to have more texture to it. This is what's called a diamond ground pavement. So this is actually an operation that's done after the concrete set, so there is cost associated with it. But even though it looks like it has more texture, it's actually quieter, slightly quieter than the very smooth pavement. So it's, like I say, it's texture up to a point. The other thing with concrete pavements that can be an issue is the joints. Most or a lot of the concrete surfaces have periodic joints in the pavement. Sometimes these are reinforced, so they're with reinforcement rods, so they're kept essentially so they're not offset from each other. But over time, they tend to deteriorate and you get some offset between them. And there's also grooves, and these grooves can generate noise through pumping of air out of the groove. So, what this sounds like. This is actually riding with the tire, so that's the onboard sound intensity. But also, that's the sort of thing you hear inside your car, too, as you're going over concretes with faulted joints. So this does increase the noise level. This is just a time history, basically, of what I just showed you, or just played for you, both with and without joints. And there's it can be about a 2 dB difference when the joints are added into the pavement, it's shown here. And it's also because it is an impact sound, it's definitely a lot more noticeable than when they're not there. Okay, with the surveys that we've made, then the next question is, well, what do I do with that? And usually what happens is agencies will go out and do some demonstration projects or do some research projects. This just happened to be one where it was a city street in Northern California where the original is shown in the bottom right, and it was repaved, shown in the upper left, producing a 6 dB reduction. This is pretty interesting because it was a relatively low speed pavement, somewhere probably around 50 kilometer per hour range. One of the earlier demonstration projects that was done in the state of California is shown here. There was an old dense grade asphalt surface, it's shown in the upper left, on a major interstate between San Francisco and Sacramento in Northern California. This was overlaid with a porous open graded asphalt. And I'll play the differences for you here too. Now again, with the overlay. There should be two things that are obvious about these pavements. Can I get this one to stop? Okay. Is not only is the level lower, but there's also a very definite frequency shift out of the high frequencies into the low frequencies. And generally, that seems to be more pleasing to people that live alongside a highway to have the lower frequency. If we look at that in terms of spectra, I think it's my first spectral plot, but for those of you who aren't familiar with this is a third octave band, it's called, so it's a constant percentage bandwidth in terms of frequency. And the frequency is on the lower scale, and the sound pressure is on the vertical scale. And this is from a wayside measurement, basically. Anyway, the reduction that's shown here, the baseline was the old asphalt and then the newer open grade. Overall, the level was about 6 dB quieter, but you can also see that you can see that frequency dependence. Essentially, the level above at 800 hertz and above is just remarkably reduced. In some areas, almost about 10 dB. And this makes the effect of the overlay much more dramatic as you listen to it than just strictly the overall level. There was also research work done in California looking at the quieter versions of concrete. I showed you some examples earlier. This was a number of 11 different test sections that were built on essentially a new highway out in the middle of the desert, as you can tell. It was first tested in 2003. This just shows some of the levels. Just all I'm showing here is that these are quieter surfaces, and that one ground surface that I showed you is called Section 5 here, and it was the quietest of all these quieter PCC pavements. Well, with that information, the agency, Caltrans in this case, started using it in practical applications. There was a bridge deck up north of Sacramento where people were complaining about the noise. They had redone this bridge deck, and the residences to the side here were up in arms about the noise level that was created from that. So this seemed like a good application to find out what we could do with some of the techniques and texturing we learned with concrete. And I'm going to let you hear what this sounded like originally. And this you're going to hear initially, it's transitioning onto a bridge. So first there's asphalt, then there's the bridge deck, and then there's asphalt at the end. This was the original bridge deck. So I expect none of us would really like to live close to that, or even drive your car over it, for that matter. And then afterwards, same thing, it starts with the asphalt. There still was a little bit of residual that you could hear in that in terms of the transverse texturing. You can see here where the little loudspeaker is that there's still some of that left, but it was remarkably quieter. And in fact, it was about 10 dB quieter. So this was definitely really saved Caltrans in terms of these neighbors, and definitely well received. Another demonstration project was one also done in Northern California. This was a major freeway that goes north of San Francisco. And in this case, it was an older pavement that was getting to be quite noisy, and the residents along the freeway were really clamoring to have a sound wall built. And of course, that's an expensive proposition, and also it's not really usually done to an existing highway. It's usually what's done for new highways to build a sound wall. So there was definitely resistance from the agency's point of view to doing that. So the overlay was applied, and the results are shown here. These are measured at 15 meters away from the traffic on the new and old pavement. And what you see here is these are two different microphone heights, basically, on the left and the right. Was pretty much a more than a 10 dB reduction in the wayside noise level. I don't have a clip for that, but I think you can imagine what that sounds like based on the other ones. So again, a very dramatic reduction. So probably the biggest poster child, if you will, for quiet pavement was something that was done in Arizona. This is the Arizona Department of Transportation, ADOT we call it. And they did a pilot program for quiet pavement that started back around 2003. They used preliminary research to look at what pavements were quieter. The project itself consisted of overlaying 185 kilometers of highway in the greater Phoenix area. And this was coupled with initial and then long-term monitoring. The original research work that was done is shown here. This shows 5 different quieter pavements that were candidates for this overlay. And these were, some of these were developed in Europe, some were more local products. The AFR, the rubberized asphalt friction course, ARFC, is shown on the left here. This was in use in Arizona actually prior to this, but it was found to be substantially quieter than the others. And it is actually the only one that has rubber content in it. So this is essentially ground up rubber that's put into the pavement. It's thought to make the pavement softer and reduce tire noise in that method. So this looks like a good option. This just shows the implementation of it. This is a highway after the overlay on the left, and the original transverse tying concrete on the right. This was, as I mentioned, 185 kilometers of the greater Phoenix area. And I suspect most of you aren't really familiar with this, but there's a large ring of freeways that surround Phoenix, which is pretty much in the center of this diagram. There are 3 types of measurements done. OBSI measurements were done every milepost along this 185 kilometers. There were some, the green spots are measurements made in people's backyards or kind of where people live. And then the blue is our research sites, where the sites were level with a clear field of view of the highway, so there was no, shouldn't have been any issue about what you're measuring. So here again, the reductions were pretty substantial. The pavement was pretty noisy that was there because it was all transverse tine PCC, but we're looking at somewhere typically 8 to 11 dB noise reduction from the overlay. I'm showing here the wayside, which is a darker blue, and then also the onboard source levels. So in this case, the source level reduction pretty much carries over to the wayside. Okay, so we know we can make things quieter with quieter pavement, but in terms of implementing it, the real issue is how long does it stay quiet? And this shows some test sections that were measured in 2002 and then 2008 and then ongoing from there. But you might get an idea when you look at the pavements why the lower one's noisier by 2 dB. To get a better understanding of that, we did testing at the NCAT test track, which is the National Center for Asphalt Technology. And here it's a pretty neat facility. They have heavy-duty trucks running 24 hours a day around this test track. It has over 50 asphalt surfaces, and they can measure all kinds of properties of it over the time they do these durability, if you will, testing on it. So one thing they have that's interesting is they have pavements that are identical but different ages. So what I'm showing here are two different pavements. These are with the same design. Basically, they're 9.5 millimeter maximum aggregate size. And you can see they're different from each other. So we quantify that a bit more. It's shown here with these different pavements. The dark blue are new pavements of the same design, and then the darker orange ones are old pavements of the same design. So, and then also I'm showing you the porous pavements in there, similar to the porous pavements that we measured in the I-80 Davis study I talked about before. Well, if you go and average these, it comes into three groupings that I like to call the old, the new, and the porous. The new is interesting in that it does have accentuated high frequency noise, which depending on who you talk to, that could be due either to frictional properties or to air pumping from the tread, in the sense that as aggregates, there's not much aggregate exposed, so it's a very smooth surface. So it could tend to emphasize air pumping. Anyway, as the pavement gets older, you can see what happens is that the aggregate gets exposed and it starts generating lower frequency noise. So that's what we're seeing here. For the porous, though, it's quite unique in that the levels are reduced, as we saw before, in the higher frequencies, starting at about 1,000 hertz. In the lower frequencies, it's a bit higher, and this is because typically what a lot of agencies will do to make a pavement porous is to increase the size of the aggregate so there's more spacing in between the different stones and the essentially more penetration of air into the pavement. This is some examples of worn pavements. The upper left is one that's actually produced by a machine. They essentially run a tire in the same track over and over again. It's loaded with this machine and does that. And what you can see there is that in the path of the tread, which is between the arrows there, the aggregate is much more exposed than it is outside of the patch. So this is one of the dominant things, really, particularly for asphalt, that causes increased noise level with time, is this loss of aggregate, or what's typically called raveling of the pavement. And this just introduces more positive texture that the tire sees. Another example is shown in the lower right. This was just a naturally worn pavement in the subdivision where I used to live. And it's a very noisy pavement. It's also one of the things you can find in all these cases is a sure sign of a pavement aging is when you see aggregate to the side of the road, where essentially these are just stones that got dislodged from the pavement and cast out to the side. So getting back to the porous pavement, these are measurements that try and replicate the propagation of sound over a porous pavement. We have a small loudspeaker source representing a tire on the ground, is in the foreground of the picture on the right. And what's shown then is the difference in level between a non-porous pavement and a porous pavement. And what you see is a large amount of attenuation when it's propagating over the porous pavement, particularly in the frequency range that we've been talking about for porous pavements, so somewhere around 1,000 to 2,500 hertz. So you can actually, just to demonstrate this, you can actually take that attenuation and apply it to an actual pavement in terms of its spectrum. That's what's shown here. The green is actually the rubberized asphalt from Arizona, but with that reduction applied to it. So this is simulating a measurement at a wayside measurement at 25 feet and 50 feet away from a porous pavement. It turns out the Arizona pavement is not porous. It is just quiet, and some attribute that to being the rubber or just the actual mix design in terms of the stone size. This just goes back to the Davis and the porous asphalt, but we can see the gray line is a non-porous and the other colors are porous pavements, and we see this reduction in the higher frequencies. Getting back to the Davis study, this shows what's happened to that pavement over the years. The last measurement made there was after it had been in service for 16 years. And what you see is a couple of things. First, you do see the increase in the low frequency. There was a lot of raveling on this pavement as time went on. And you also see increases in the high frequencies. And this is most likely due to some of the pores of the pavement clogging over time. Particles get in there, and essentially it doesn't have the porosity that it started out with. But there's still quite a bit of reduction in those high frequencies. So it still has that character in terms of the sound that we listened to before. At this point in time, the pavements are about the same in terms of overall noise level. Going on to concrete pavement, those sections that I showed you before out in the desert in California were measured over time also. And this happens to be one of the ground sections, one of the quieter sections. And it's kind of interesting what you see here is the lower frequencies are not much affected over time. This is a 9-year time span, but you see quite a bit of increase in the higher frequencies. If you look at those increases in each of the bands, this is this is taking the data for each band and fitting a linear regression through it. So it's time level versus time. So the plot is dB per year on the y-axis, and then the frequency band on the left. And what you see is this definite bias towards increasing the noise or the rate of decline of the pavement centered in the higher frequencies, particularly around 2,500 hertz. So what's going on here? The one thing you can see from looking at this pavement in more detail is initially the pavement had some texture to it. It had longitudinal grooving in it, and it also had more texture in the surface itself. After time, what happens is the surface polishes, loses friction. Very often there's concern about rehabilitating it because of loss of friction. So that's one of the mechanisms that's going on with quieter concrete. There are other effects too. Certainly increased roughness on the joint slap we talked about before. One of the other things that can really tear up concrete is chains instead of snow tires. So these tires or these pavements can deteriorate very rapidly if there is a lot of use of chains instead of snow tires. In Arizona, this shows what happened after 8 years. You can see a couple things. You look real closely in 2012, the aggregate is a bit more exposed, so it's a bit rougher surface than it was before. And also the joints are creeping up. The concrete joints are essentially propagating up from the surface, and we see now this slap, slap, slap again that we listened to with the concrete. Over time, this shows the onboard sound intensity level, and the upper curve and lower curve are 5 different sites where this was measured for wayside. And basically we're looking at about 0.4 dB per year, and the wayside deterioration a little more than that, about 5/10 of a dB, half a dB per year at the source itself. So What this does, I don't expect you to read this. I'm just going to make a few points about it. This is this is kind of a compilation of the longevity data that we had available to us from a number of different studies. A couple things to notice is that we did track the AADT, the average annual vehicle traffic basically on the pavement. So, and what we find, and this has been talked about before in other research, that the pavement tends to deteriorate more rapidly with increased traffic, and particularly with increased truck traffic. So this is just more of that data. The thing I'll draw your attention to down here is the averages between asphalt and concrete. And as you can see, the asphalt does tend to increase faster with time. So it can be quieter, but it also increases at a faster rate in terms of noise level. So assuming you've grabbed all this information, now what do you do with it? How do you actually put it into policy that can be rational and affect people's lives that live near freeways? Basically, there are two choices for abatement, or maybe combinations of choices. Sound walls are certainly, by the U.S. Federal Highway Administration, is a preferred method because it provides a reduced or a continuous amount of reduction. So if you put the sound wall up and it gives you 10 dB reduction, it's going to give you 10 dB reduction no matter what the pavement is on the other side. On the downside, the impact on neighbors to the freeway is limited to being relatively close to the barrier. So it doesn't reduce the noise levels throughout the whole community, just much more benefit for those close by. Noise levels still increase with time. Doesn't matter whether it's 10 dB lower than it was before, but if that source keeps going up, at some point you're going to be at a level that you were trying to guard against at the beginning. So it helps. I mean, it's constant, but it doesn't keep things from increasing. And they're also expensive. Building these sound walls are. And there's limits on where you can build them. If it's a hilly area, houses going up a side of a hill, for instance, the barrier won't do you any good because it won't block the line of sight. Quieter pavements. They have their initial lower cost than barriers. You can generally put down a quiet pavement relatively economically, and you do have to put down some kind of pavement to begin with anyway for a highway project. So that kind of offsets any additional cost for like a porous pavement. It gives a larger area of reduction, extends out farther pretty much throughout the whole community. It can be used anywhere. It doesn't really matter if it's on a hillside or wherever. Downside is the noise level will increase over time, which we talked about. And this requires periodic maintenance. And in this case, the maintenance, as in Arizona here, would be repaving, essentially either grinding away that surface or adding another sacrificial, quieter surface on top of it. So there is those costs. So you have to trade these off, and you need the data. One of them is the pavement data we've been talking about, the initial reduction and then the longevity. For the barrier, you need to know how high you're going to build it and what the square footage is going to be. This is one of my colleagues standing next to a barrier in Phoenix. And this might be a little bit out of control in terms of the size of the barrier. But anyway, so there's and then the other part you need is cost data. What's the initial cost, and then an estimate of what the ongoing cost is. This requires some additional input. You need to establish your goals. How much noise do you want to reduce, and how many people do you want to impact by that reduction? You also need to be able to model that reduction, both in terms of the barrier and the pavement. So you need to be able to incorporate pavement into your prediction model, as well as the effective longevity, so that you can predict what happens towards the end of the life cycle of the quieter pavement. There are tools to apply to analyzing this, life cycle cost analysis, where you look at trade-off, essentially the initial cost of the barrier compared to the ongoing cost of maintaining the quiet pavement. Pretty simply, you just put all this together, you figure out which gives you the most bang for the buck, which gives you the lowest overall cost with the most reduction and most impact on people living near the highway. This is outlined in a study that was done some time ago. This was actually a workshop and an I-INCE symposium that was sponsored a few years back, and looking at methods of doing this kind of cost-benefit analysis for barriers. There's also is available on the web. I think there might be a link to it, well, there is, on the I-INCE USA website, if you're interested. For more information, that's going to be, we've just completed putting together a quieter pavement, essentially manual for the state of California, and that's going to be on the web, on the Caltrans website soon, I understand. So it would be another source of some of this information I've been sharing with you. So I don't really have any conclusions because I don't know what you can conclude from this, other than that there are things you can do, and it takes having a whole approach to actually do the implementation, looking at the data, the longevity, the initial reduction costs, and trading it off with these barriers. So with that, thank you for your attention.
Okay, time for one or two questions. I think we need either the microphone or we will need to rephrase the question here, or both.
Thanks for this beautiful presentation. My question is, from the slides, seems that some of the analysis refers to a few years ago. How maybe the improvement of the performance of the tires can affect in this result? Because some models of tires have maybe 5, 6, 7 dB of difference, and is a quite large improvement and can maybe reduce the cost of other things.
So I think you're asking quieter tires, are they making a difference, basically? They certainly can. I have not seen a lot of data to support that there are quieter tires out there at this point. And generally, our test tire is a relatively quiet tire. But there are advances that can be made in that area. The one thing I didn't really talk about too much is when you have a noisier pavement, it doesn't really matter what the tire is doing. It's really the pavement that's causing the increased noise.
Okay. Another question? Okay, so if there are no questions, I'm going to pose a hypothetical question. So, Paul, where do you see this going in 5 or 10 years? Assuming somebody else will do it.
I think there's still a lot to be done, and you can see that from the sessions that we have here at Internoise. There's always at least almost one session a day, and sometimes there's a whole string of sessions that last the whole time. So there's plenty of research topics to be dealt with on tires itself. We still don't have a really good, especially high frequency model. There's a lot of work on vibration of tires, and even that is, I won't say incomplete, but there's still work to be done there too. And then for higher frequency, that's a much more complex topic that could benefit from some research for sure.
Okay, with this we'll conclude the session, so if you can give him a big hand.